you hear me now? Can you hear me now? Um, hello, hello, hello. Christ, let me check my phone if I can hear myself. Oh, all right. Okay, sorry about the no sound. I didn't know my mic was disconnected. Oh, my bad. Sorry, guys. Sorry. Okay, so I hope you guys are doing well. Yeah, welcome to the place where I struggle to solve lead code questions. All right. I still did not bring my. All right. Okay. So sorry. I'm back again. I was honestly not prepared at all. Oh, okay. It's not going to be 30 minutes. I can increase the time at least. Let me do 40 minutes. 40 minutes will be better, right? Because uh, time is really not on my side now. I have a project to finish, so I'm just stealing time to stream. All right. Okay, so let's bring this cable here and connect it to the tablet to write on the screen. So we'll write on the screen with this. Yep. So let's go. All right. So here's an interesting question. Second minimum node in a binary tree. Now, to solve binary tree questions, I would always advise. Um, I would always advise you know. I'm not really an expert with binary trees, but what I've seen so far, there is a prerequisite to for binary trees, right? At least the easy part, you need to know about recursion a lot. You need to know how to recursively call a function, how to, manage your base cases within your recursion so that you don't, end up with an infinite call to your function. I think there is a question for me, so would you explain where we should use stack? I know it works, but I don't know where to use it. You mean stack the data structure? Um, okay, that's true. I think I should answer it at the end, but I'm not sure about your question. Can you ask the question again? You mean stack the data structure or stack within this question? I don't think you can use stack in this question. It's a binary tree question, but please can you rephrase your question and ask it again? I will make an effort to answer it later at the end of the explanation. All right, so moving on. We have this question here, which is an interesting question, and I solved this yesterday. So I'll just go over this question and explain it. And we have two other questions as well to solve, right? There is this square of sorted arrays, which I was trying earlier, but then I did not read the question properly to actually know what the question was saying. But anyways, we'll look at square root x as well, right? So, yeah, let's get started, right? So we are given a binary tree, right? Given a non-empty special binary tree consisting of nodes with the non-negative value, where each node in the tree has exactly, hold on, it seems my network is a bit off. All right, I think I'm back now. Okay, so where each node in this tree has exactly 2 or 0 subnode. If the node has 2 subnode, then the node's value is the smaller value amongst its 2 subnodes. More formally, the property of root.value is equal to the minimum between the root left node and the root right node. Given such a binary tree, you need to output the second minimum value in the set made up all node value in the whole tree. If no such second minimum exists, return -1. Okay, so the question is asking us to find the second minimum value, and the reason why it is called second minimum value is because usually the first node we see in the tree, right, is assumed to be the first minimum value for some reasons, but because this question is giving us an input which is a special binary tree, so we can actually understand that, okay, the first node, which is the root node, is the first minimum value we see in the tree. Now, how do we find the second minimum value? Well, we can use a depth first search approach where we traverse the left subtree and the right subtree sequentially. So first of all, we'll traverse the left subtree and find if the left subtree, right, has any node that, respects this condition, right, that fits into this condition. And the condition is such that the value of that node has to be less than its right and left node, right? So again, in this picture, you can see the right child of the root node is 2, right, which is the a node in this tree. But this node here does not have a left and right child nodes, right? So automatically, this node is what we call a leaf node, right? So a leaf node usually possess 0 nodes, right? So it's the last node in the tree. So we leave this case this side of the tree and we traverse this part. So you know what, let me use this image here. So we start from this point, right? So we'll use this as our root node, right? And then we'll do a depth first search from the root node down to the left subtree until we meet the last node in the tree. Now, with the way this question is set is such that the condition is that one of the nodes in this tree, aside from the root, right, will have either exactly two node, which is the right and left child node for that particular node, or 0 nodes. So meaning if there is no node here, then we don't have to continue our depth first search, right? So we stop at this point. There is no need for us to continue. So you will not get a situation where a node will have just one child node like this, right? This is impossible. So based on the question, right? So we need to keep that in mind. So we do a depth first search, right? Traversing the tree from this point to this point. So this will not be our second minimum because it doesn't have a left and right child node. Then we do the same thing for this place, right? So when we get to this point, we can see that this node here has a left child and a right child. So since it has the left and right child node, and the value of this node, right, fits into this condition, right? So root.value is equal to the minimum between these two, right? And the minimum between these two, the minimum between this 5 and 7, which are child node of this node here, is 5, right? So meaning the second minimum node we have in this tree will be equal to 5. We can check another case here, right? In this case here, we don't have any second minimum value, so we return -1 as the question indicated on this line here. So how does our depth first search work, or what were the steps taken to solve this question? Well, first of all, we needed to know, we needed to set aside the root itself, the root node from the tree, and then take the next nodes, right, or the children node of this root node as the points or the nodes at which we need to perform the depth first search. So again, we'll start at this position, right? We'll start here, and then we'll set this aside as our current root node. So this will be our root node set aside, and then we'll treat these nodes here, right, as the current root node, or let's call them independent nodes, right? Independent root nodes. And this is where we need to check the condition for whether this node has a left and right child, and the minimum value between those children is equal to this node here. So I'll show you the code for this and explain further. So let me bring this here. Now you can see, first of all, I set the second minimum value to an infinity value. Now the reason for this is because we know the highest possible number we can have is this, right? But it should also be the second minimum in the tree. So when we see the second minimum, we'll replace this value with that second minimum. So this is just a placeholder for our second minimum, right? So we'll do this, and then because we are going to return that second minimum as a single value itself, which is what the function is expecting, right? If you look here, you can see we are expected to return an integer. So I set the found flag here, right, to indicate if I had found that node or not. Now here is where it has become interesting. This is the depth first search code, right, where we perform the depth first search. Now the condition is such that the node's value has to be between the second minimum value has to be between the first minimum, which is our root value, right, and less than any previous minimum we've seen. In the case where we've seen a minimum in the past, we need to set the second minimum, and that's likely going to be in the left or right subtree, wherever we see, but we traverse the left subtree first. But in the case where we found a minimum previously, right, and we want to set a new minimum, a new second minimum, then that minimum has to be within or fall within this condition, right? Now you can even set, you can say, if you can even use the actual template the question gave us, right? We can just say if the minimum, so we can say if node value, right, node dot value, okay, is equal to the minimum between those two, its left and right child nodes, right? We can do this as well. We can say node dot, hold on, this is a tree node, okay. All right, if node dot value is equal, not an assignment, all right, is equal to the minimum between the node dot right, okay, and node dot right, let's do left and right. So node dot left dot value, right, and node dot right dot value. Okay, this is also the condition for us to set the second minimum. So second minimum will now become that node, right, that fits into this condition, and we can set it here. Now you can see we recall this depth first search, right? This is a function. So depth first search is going to be called recursively. Now this is a helper function that I created for our main function itself, right? So we'll use the depth first search method, right? We'll call it recursively by passing the current node's left value and the right value. So this will perform a pre-order traversal, right? So, and every time we get to a node, we can find out this, right? But the best suited case for this is this particular if statement here, because the first min was initially set, which was the root value, right? And you know what? It's good to test this out. Let me see whether this will work. So I'll just bring this back here. Let's take this a little bit. Okay. So if node value is between these, right, we can set second minimum value here. Let's see if this will work. Okay, so this did not occur to me yesterday because I was, spending a lot of time thinking about the problem. Let's just see what we'll have here. If I use this and second minimum, okay, let's just replace that and see. No attributes val. Exactly. So we are not, the reason why this will not work is because, is it val or value? Okay. The reason why this did not work is because we are not sure, right, if the current node even has a left and right child node, right? So, which is why we need to set we need to use the previous condition such that the current node value has to be superior to our root node value, right, which was the first minimum, but less than the second minimum we found. In this case, we started with a floating number, right, which is infinity, right, which is infinity. So we use infinity here. It's not really a floating number, but this is infinity. What this is how you write infinity in Python. All right, so in this case, yeah, I think this is what I did yesterday. Yes, okay, so this is it. So when we found the second minimum value, right, you can either use a flag or you can use this this float here, right? You can say if the second minimum is less than the floating number, which means we've reset the second minimum at some point while depth first searching the tree. And if that's the case, we return the second minimum, otherwise we return none. And if you prefer, you can use the flag, right? We can say if found, right, if we found the second minimum, then if we found the second minimum, then we can set the value. So we can just put found here. All right, return second minimum if found, else return -1. Right, you can see we have found, which is a boolean, right? So with this condition, we can properly return our second minimum from the tree. Okay, so that's it for this question. I'll just go back here and correct this, as this will not work because we don't know, we are not guaranteed that the node with every node we visit in the tree has a left and right child node. Okay, so let's move on to the next question. All right. So before I move on to the next question, let me answer some questions here. Okay, Mike Khan was asking, okay, yes, the stack data structure. Well, the stack data structure is very useful for many things, right? An example is for operations that are first in, last out, right? So when you insert something in a stack for the first time, and that thing is the will become the last thing you remove from the stack, right? Sorry, what? Okay, so yes, first in, last out. So let me quickly represent that so I'm not saying rubbish. Let me be sure. So we have a stack like this. So imagine this is our stack. Where did I drop this? All right. So imagine this is our stack, right? Here. So if you insert an item in the stack, let's say you insert 1, right? And then you put in 2, 3. The last item inserted in the stack will be the first to be removed, right? Even when you look at, so an application for stacks, right, will be just what I just did, right? So let me go back again. I drew a stack, right? This is our stack. I inserted 1 and then 2, then 3. But when I press Ctrl Z, right, I remove the last item from the stack, right? And I press Ctrl Z again, Ctrl Z again. So last in, first out. So last in, first out. LIFO. So, and an application, a reward application for stacks will be to implement a redo, and undo operation, right? This will be a very good use case for stack. I wasn't even thinking about it until I just wrote something on the screen and undo it. So undo and redo is a very good problem to using stack, right? So you can use stack to implement an undo and redo feature in your application. So that's one of the use cases for stack in a list of many use cases, right? So yeah, if you can implement a redo and undo functionality in your application, let's say you build a web application, right? And the user does something. The user, let's say you build for example, a to-do list. You can start with a simple to-do list, right? And then the user adds a to-do to their list, right? So let's say they add this to-do to the list. So I'll say 1, and then they add a second to-do and so on, right? But you can have a function, I mean, a button here that deletes the to-do. But if the user wants to delete the recently added to do, you can implement in your function, in your code or your program, that when they click Control Z, right, when they click Control plus Z, then the last to do they added to their to do list will be removed. That will be an interesting use case for stack, right? So I think you should try that as one of the many use cases for stack, right? So that will be very useful. Okay, so let's try a different question. I hope that answers your question, Mike Khan. If you're still here, please signal you've heard my solution. Okay, so let's continue with the questions I have for today, and that would be aha. So this question, I was still trying to solve it when I just ran out of time to stream, but we'll look at this now. So given an integer array nums sorted in non-decreasing order, and this is the part sorted in non-decreasing order, return an array of squares of each number sorted in non-decreasing order as well. I don't know why they made all the other parts were highlighted, and this part, which is the most important one, was not highlighted. And this was something I didn't read very well, and I was trying to solve the question right away. So we are given an input array, and we want to sort the array in the same order it was given to us in. Now, we are not only sorting the array, but we are returning the squares of the sorted form of that array. So we need to square each integer in the array and then return it in the same order, right, which is non-decreasing order. So increasing order in this case, from smallest to biggest. And if you look at the output here, right, you can see we start off with -4, 1, which is less than which is superior to -4. -1 is less than 0, and then we have 3 and 10. So when we square all of these, right, we need to return them in a non-decreasing order, which is increasing order. So we'll start with 0, 1, 9. 9 is the square root of 3. Is the square of 3. 4 is the square of 16 is the square of 4, -4 in this case, and 100 is the square of 10. Now, one really I would say, like, there's an important thing to notice about this question. Now, when you look at the squares of the numbers, right, initially -4 was the smallest number, right, in the nums array, but after squaring it, it becomes 16. So meaning we are not going to expect the squares to work in this way. So here is what I was doing. I was just trying to swap the values as I'm squaring through, which is not going to work, right? This isn't what the question was asking. The question was asking to square each value in the nums array, and then return the nums array itself in a non-decreasing order, so from smallest value to biggest value. So now the original order was this. This would have been the case if this was going to work, but after squaring negative numbers, we get a positive number. So that is one of the most important things to really note about this question. So how do we do this? How do we square the values, right, and then return them in a non-decreasing order? So I was using 2 pointers, which is what I'm still going to use anyway. I was using 2 pointers to target the values, right, the smallest values, square them, and then swap their position. But this isn't really going to work, and we can't mutate, or we can't replace the value in place. At least for now, I've not really thought about replacing the value in place. But again, what we need to do is we need to square the values, right, and add from the end. So we can start from this place, right? So we can square this, right, and insert it into a new array, right, and then return that array at the end after visiting all the numbers in our nums array here. So that's what we are going to do now, and I will just come here and give a quick explanation or a quick demo of my thoughts on this question. So we have an array like this, which is our input array nums, and then we put this here. Okay, so we would increase this like this so that we can see what's going on. Now, what we'll do is we'll use a double pointer method, right? I'll create another array called results, and we'll insert the values into results. So we can do something like this. We can do something like this. And here All right. So we'll start with this. Since this is in a non-decreasing order, we know our largest values. Our largest value is at the end, so we'll have our right pointer here and our left pointer at the beginning. All right. So with these, we can begin to shift the values, right, uh, as we iterate through the array, or as we, shift the pointers through the input array. So um I'll create a new array called results. Like I said, result is going to have as many values we have initially here. So in this case we have we have 5 values in this array, so 5 integers here. All right. So we start at this position, right? Now we need to make a comparison between these two values, right? The reason why we need to do that is because negative values, after squaring them, they become positive values, right? So this means we are likely to get a larger value, if at this position after squaring them, even though the value here was initially the smallest in the original array. So we take this, right? We take this, so this is the left pointer, this at position left, and then we say this squared, right? I mean, we don't do square, but we can do that and compare it with this. But in this case, we can also use the absolute value, right, and compare the absolute value of the two. Either cases work, but I'll use the absolute value solution. So here we'll have -4, right? The absolute value of -4 will be 4, right? This is going to 4, and we'll compare 4 to the absolute value of 10, which is equal to 10 again, right? So we have 10 here. This will be 10. So we'll check if this is superior to 10, right? Which is also the absolute value of 10. So in this case, this is not the largest value, right? 4 is not the larger value, so this will be our larger value, right? So we'll take this, we'll square it, right? This is going to be equal to 100, and we add 100 to our results, right? So since we are going to have it in a non-decreasing order, right, which means the smallest value will have to appear in front and the larger values will be at the end. So we'll put 10 somewhere here. So let me draw some lines. I'll remove all of these. So let me say this is going to be like this, and we'll begin inserting the values at each point. So this is going to be 100 here, right? And then after finding the current value and inserting it here, we'll shift the pointer, right? We'll shift it away from this point. So we'll remove R from here, right, and put it here. Okay, and we'll do the same thing. We'll find the absolute value, right, and then compare the absolute value between these two. So in this case, we have 4. The absolute value of 4 is 4. 3 is 3. 4 is superior to 3, so 16 will come here because -4 squared is 16. So we'll put 16 here, and then we shift this from here, right? We shift it to this point, and we'll do the same thing here, but in this case we'll have 9. 9 is our next value. We'll put 9 here, and then we'll shift this from here, from this point to this point, right? So we'll have here -1 squared is 1, and then this will move from here to here, right? And this is going to be 0 squared, so we'll put 0 here. All right, so that's how we'll be able to sort this array and return the squares of of the integers in the array. Now, before I pass on to the code, right, I will explain the second solution, the second question, and then we'll begin writing the code for both of them. But before I even do that, let me check if there are any questions for me. So here we have hello comfort. So people are counting my days more than me. The days left, not my days. All right, so yes, the Google, the to Google. When it is ordered there, I'll send him one. All right. Okay, so let's continue. I think YouTube should solve this issue with the reaction button blocking some of the comments. It's really annoying. Okay, so all right, so we want to look for the square root of a number, right? The square root of a number. So um to do that, we need to so let's read this question. I think there's another question for me. So what's annoying? Oh, the reaction button blocks some of the text, right? On YouTube. So when you send a message, some part of the message is blocked by this big, I don't know, with the emoji in it. So it's really hard to see all the text at once. So I have to like shift it away and adjust the screen to see it. Yeah, that's what is annoying about YouTube. All right, so let's continue with the questions. Oh my god, I have just 4 minutes left. Wow. You know what? I let me try my best to explain. I don't know why the time is really running fast. I don't understand it at all. I've seen your heart. Thank you very much. So, now giving a non-negative integer x, let me close the chat for now. A non-negative integer x, return the square root of x rounded down to the nearest integer. The returned integer should be non-negative as well. You must not use any built-in component, any built-in exponent function or operator. For example, we do not use the power x. When you do a number to the power of half, it will return the square root of that number. So you shouldn't do that. In C++, wow. And then in Python, you should not do this as well. That's very interesting. So I've actually seen this question some time ago on YouTube, and there's this guy. I've forgotten his name. Um, he solves lead code question, and he does this short. And I saw him. He used a binary search, right, to solve this question. But I'm going to, you know, go a different route. I'm not saying my solution will be the best, but I wanted to really, make certain things clear, right? So first of all, we are still going to use we are going to do a brute force solution, right? We will try a brute force way. Now the brute force solution will be such that since we are searching so let's say for example, right, the square root, we are going to look for the square root of 4, right? Now the square root of 4 is any number less than 4. Is the square of any number and the square of that number should be less than 4, right? So if we did something like this, so let's say we iterate through every number within that range. So we'll iterate from 0 all the way to 4, right? Now maybe 1 less than 4 in this case. So we can see within this range we have 0, 1, 2, 3, and yeah, so 4 will not include 4 because it's the value we are trying to search the square root of. Now if we square each one of these numbers, right, if we square each one of these number, the answer we get should be less or equal to 4, and that number becomes the square of 4, right? So we can say here this is going to be 0, 1, 2, and oh, sorry, I was using squares. So square of 0, right? They will do this squared is 1 squared, 2 squared, and 3 squared. Now we'll keep track of the squares, obviously. So and we'll compare the square to 4 and see if that's the value we are looking for. So in this case, we'll have 0. 0 squared is 0, right? 0 squared is 0. Sorry, is 0. 1 squared is 1. 2 squared is 4. 3 squared is 9. Now 9 is superior to 4, right? So 3 cannot be the square of 4. But 4 is equal to 4, right? So 2 is possibly the square of 4, the square root of 4, sorry, the square root of 4, not the square of 4. So that is the brute force solution for this question, right? Now another way to do this, which is what I've seen online, is to use a binary search. And how would a binary search work for this case? Now the reason why you have to use a binary search is because of very huge or big inputs like this, right? So we don't want to our solution is going to be O of n, right? The brute force solution is going to be O of n, but it is not really efficient in this case. So O of n meaning the largest input, right? If this was 2 million, right? If this was 2 million, right? This is what 20,000. If this was 2 million, we'll still wait, this is 200,000. So 2 million. I don't know why I used 2 million for this example. But if this was 2 million, we'll have to iterate 2 billion times, which is not good, right? This is not a very good solution. Now, with a binary search, we constantly divide our input into halves and search within that half. So we'll have a left and right pointer for our binary search, obviously. Now, the left pointer is going to be at the first integer. We'll set it to 0, right? So let's take, for example, in this case, 8. So we'll have numbers from 0 all the way to 7, right? But we are going to use a binary search in this case. We are not going to use our brute force solution. So here we'll have r equal to 8 minus 1, which is equal to 7. So now we'll find the midpoint between these two, right? So the midpoint will be 7 divided by 2. So we'll round that up. This will be equal to 3, right? Now 3 is our current value. So is 3 squared superior to our input here? If it is, then it means we need to shift our right pointer down, right? So we'll do r is equal to just the way we look for binary search, right? We use a binary search, we find the midpoint, and we reset the right pointer if the current midpoint is superior to our target. So here we'll say r is equal to the midpoint minus 1. So in this case, midpoint was 3, right? Midpoint was 3, so we do midpoint minus 1. So r is now equal to 2, right? So we'll do 2 plus this, and we'll say 2 squared, right? So okay, I'm just writing this in in any order. Sorry, let me properly go through this. So we are going to use a binary search, right? So we are looking for the square root of 8. Now the square root of 8 will be any number less than 8, right? Less than 8. So I'll just put n, and any number squared should be less than 8, right? That's the only thing we need to know. So if we use a binary search, we'll need a left and right pointer. So our left pointer is going to be equal to 0. Our right pointer is going to be equal to 7, right? 8 minus 1. Now here's how the binary search plays. We first of all search for the midpoint, right? So the midpoint or the mid value will be left plus right divided by 2. So this is 7 plus 0 divided by 2. This is 3.5, but we'll use 3 in this case. Now 3 is now our current mid value. Now if we do 3 squared and that value is is less than 8, then 3 is the square root of 8, but 3 squared is equal to 9. So 3 is not the square root of 8, right? So we continue. So we reduce, since we had a value superior to 8, we'll reduce our right pointer, right? So we'll say r is equal to m, which is the mid value, minus 1, and this is going to be equal to 2. So our r becomes 2 in this case, right? And then we'll do the same thing. So we'll say 2 divided by 2 is 1, right? This is our midpoint. 1 squared is equal to 1, and 1 squared is still less than what do you call it, than our input, which is 8. So we increase the left pointer, right? In this case, L is going to be equal to the midpoint plus 1. So L is going to be 2. So we'll do 2 plus 2 divided by 2. So 2 plus 2 is equal to 4. Divided by 2 is 2 again. So we have 2. So 2 squared is equal to 4, right? Now, is 4 less than 8? Yes, 4 is less than 8. So 2 could be a possible solution in this case. So we need to do this until the left and right pointer are equal, right? And when they become equal, we can return either the left or right. So in this case, right, 2 that we found here, so our loop will stop at this point because right is equal to 2 and left is equal to 2. So meaning our mid value here is going to be equal to 2, right? So 2 is the only possible value that is nearest to the square root of 8. Now this, I'm not saying the square root of 8 is equal to 2. It could be more than that, but our loop terminated at this point, so we say 2 is now our current minimum, the square root of 8, our square root that we're looking for. So this is going to be the answer here. All right, so I think I'm out of time. So let's see if there are any questions. Hello, Numan. Welcome to the stream. I agree, time really goes fast. Yeah, exactly. Our school has 3 months of holidays from June to September. To be more precise. Oh, wow. Anyways, you'll be going back to school very soon. Wow, that would be really awesome. Right. University, right? You're in university or high school? You're studying maths. I think you told me you were studying maths. All right, so let's continue. I'm going to provide the solution to. I can't stay any longer than 10 minutes. Let me just add 10 minutes to the time, just for the sake of of my beautiful friends on the internet. So let's do 10 more minutes. I really haven't got the time. I just had uh it's a lot on my plate right now. I'm not even sure I can finish this, but let's see what we can do. Let's see. We have um what do we have here? I think the first question was what is an on come on, squares of sorted array. So this would be in the category of binary search because I'm using 2 pointers. Okay, 2 pointers and sorting. All right, that's fair. We are not sorting anything, so we'll just put it in 2 pointers. What number of question is this? 99977 squares of sorted squares. Okay, 977 sorted squares. So 2 pointers. Where's 2 pointers? Oh, I've not solved a lot of questions in 2 pointers. That's that's not nice. Lit dash 977 sorted squares. Okay. All right. So let's do this. Let's do this now. Um. So I'll copy this. This is what I was doing before. Obviously, this was wrong. I needed to correct this. Okay, let's remove this part and remove this part also. This. Oh, no, 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 no. We did not need to remove it at all. Ah, sorry about that. I needed to import it. So I think from typing, import. Ah, that was scary. Import list. All right, so we'll need a left and right pointer, right? We'll need a new array. I'll call this results. Res is going to be equal to so we'll create an array with empty spaces, right? And do this times the length of the numbers, right? So I can set this n should be equal to length of nums since I'm going to use it in multiple places. So I'll just take this like this and put it here and put n here like this, right? That's a lot of space. Then I can multiply this by n and I will do this res here. All right, I think that's it. And okay, so I'll say since we are going to keep the same order, which is the non-decreasing order, so we keep it in an ascending order. The first, we can use some condition to find the biggest number and then insert it at that point. So we can say here, we can say I'll call this index, right? Index is going to be n minus 1. So this index is what we are going to use to insert values into res, right? So let's do it this way. I don't like this space. I don't know why. It just looks somehow to me. All right. So let's say here, while the left is less or equal to right, we'll do this. So say if the absolute value of the number nums at left, which is L. Okay, we are using left and right. Left is superior, right, to the number at right. You know what? Let's do right first. So if this is, nah, it doesn't matter. Let's do it this way. ABS of nums at R, right? Then we can say res at position, right? Position, sorry, res at index. We can use index is equal to the current value squared, right? So we'll say num at L. We want the largest value, so we'll use yeah, we'll say here this R here squared. So you can do something like this. And then we shift the right pointer down, right? So say R. You know what? There's no need for me to be writing R. I can just put right and right here. Right. And then right here as well. Put left to be a bit more descriptive, left as well. And then we say right minus equal 1. Okay. Oh, I'm still using R here, so this is going to be right, and then right here. Okay, minus equal 1. Otherwise, if we use the left, so say else, if it was the left that was superior, then we'll just say res at index, right, is going to be equal to it's going to be equal to nums at left squared. So this is going to be left squared, right? 2 like this, and we say left plus equal 1, and then we can return, we decrease the index, so say index minus equal 1. All right, and then we return the result instead. So we'll say results like this. So this will be our result. We increment blah 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 blah, blah. Index. What's going on here? Typo in Word, rename to. Come on, I don't know why this. Can't you just mind your business? I wrote it myself. Stop suggesting. Okay. Let's see. I think I heard there were some notification. Oh, finally Dan is here. Welcome Dan. Ransom said he's in 11th grade then to university. Oh, okay. Nice. Find the value of function y is equal to 69 cos blah 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 blah. That's correct. That is correct. I said I'm dizzy. Very, very easy, by the way. Great and mighty EGE. Yeah. I don't even know what that is. I was also doing maths at some point, but I stopped because I needed to work. So I chose work over school. Anyways, here we are. Oh, let's draw this and see. Is the 10 minutes done? Wow. The time I set now just Oh, wait a minute. What's going on? What? Oh, okay. Okay, so I did a mistake here. This is supposed to be left and not right. And this will be right. Right. I made a mistake. So let's run this again. What? What's going on? Oh, okay. So we're increasing left here. That is my fault. Plus and right here. All right, so this worked. O of n, by the way. What? 14. Well, I don't think. I mean, okay, that's fair enough. That's fair enough. That's really fair enough. That's fair enough. Ah, you guys, the Lord be with you. You can open English version. I think you will do that. EGE exam. What's EGE exam? EGE exam in Russia. Oh, okay. EGE Russia. Rush. Oh, yeah. Unified States exam. How do you say this? I can't read Russian. Nope. Oh, so let's say git add git comment commit. So this is lead code. This is two pointers and lead dash one and 977. So let's solve the next question and I'll be off to work. So the next question is a binary search question. I'll implement the, oh my god. Guys, I think I need to go now. Um I will call you. I'll stream again tomorrow, right? Okay, that says run it again. I see it improving. Let's see. Let's see if that's going to work. We're at 14 before, right? Oh, 23. You see, this is why I really don't like Leeds Code's uh rating. So let me push this code. I'll write the code push origin main. I need to go now, right? I need to go. Guys, we'll continue tomorrow. We'll continue tomorrow. Take care. Bye.